Uh, Hello, this is Khamalesh Kumar, and I'm currently doing EE267 computer vision with AI applications. I'm here to present my project on swimmer segmentation and post estimation using motion analysis and using the deep model that is YOLOV8 and Meta SAM. Swimming is a sport that demands precision, efficiency, and speed. Every movement, whether it's a position of the arms or the alignment of the body or the propulsion of the legs, directly impacts the swimmer's performance. However, analyzing these movements for a better positioning and for the better improvement of the person's track record has been traditionally relied on manual techniques such as video observations of the previous performing athletes by the coaches. While this approach provides insight, it also makes it very subjective, time-consuming, and prone to human error. So, by introducing this motion analysis using the deep learning models such as SAM model and YOLO V8, we will be able to identify how the positioning of each joint can even improve the speeds and how detailed can each analysis can be. So, what are the challenges include in these with this? So, the challenges of swimmer motion are very unique compared to other sports. The swimmers operate in dynamic, three-dimensional environment that introduces additional complexities, and also occlusions are caused by water splashes, bubbles, and reflections can obscure key part of swimmer's body. So this makes the analysis a little more challenging to do. Moreover, the horizontal orientation of the swimmer also differs significantly from the upright postures commonly used in datasets for post-estimation models. These issues make it challenging to identify and track body parts accurately, leading to more error in analysis. To address these challenges, this project leverages cutting-edge technology that is the Meta SAM and YOLOV8. So this excels in isolating the objects from complex background, making it ideal for separating swimmers from aquatic environment. The YOLO V8, a state-of-the-art model for post-estimation, provides robust joint detection even under challenging conditions. So together, by combining these tools, we'll provide a powerful pipelining system where it can do automating swimmer motion analysis and offering a precise biomechanical feedback. So the main objective for our project is very clear. So first is we are going to develop a pipeline that automates swimmer segmentation and the pose estimation. So this will replace the manual methods traditionally used by the coaches and makes it more easier to analyze and make a better better performance for the track athletes. Second, the pipelining is designed to address the unique challenges of underwater environments, such as occlusion from water splashes, distortions, and reflections. Third, also this model seeks to provide actionable biomechanical insights that can help swimmers refine their techniques. By identifying joint positions and tracking movements, the pipeline also offers a data-driven approach to improving the stroke efficiency and the overall performance. Lastly, the project aims to achieve a superior accuracy compared to the previous models, such as like YOLO V7, demonstrating the effectiveness of integrating MetaSAM and YOLO V8. So, what are our main challenges in this swimmer analysis? So the first challenge is, as we spoke before, is the environment itself. Splashes and bubbles and reflections can obscure the visibility and makes it challenging for doing the analysis and the segmentations. And also is the swimmer's horizontal orientation. Most existing post estimation models, such as TensorFlow, MoonNet, or OpenPose, are trained on data sets where subjects are upright and makes it very easier for the analyze. That is, the environment is very favorable for the analysis condition. This discrepancy makes it difficult to adapt these models for for analyzing the swimmer questions. And also, the occlusion plays a significant effect role in the complicating in the analysis. So when a swimmer arms or legs are submerged or partially visible or overlapping, it becomes challenging for the model to detect and track the key points accurately. And final limitation of these is the limited data. There are very few annotated data sets specifically designed for swimming biomechanics. This scarcity limits the ability for existing models to generalize effectively to underwater environments. So let's go for the next thing. That is our methodology of how we're going to propose this model, how we're going to implement this model. So to overcome this challenge is the way of we are going to implement our project. So makes it as a robust methodology consisting of very four key steps. So the first is we begin with the frame extraction of pre-processing. So the video footage of swimmers performing different strokes such as backstroke, breaststrokes, and butterfly is divided into individual frames using OpenCV. To improve model robustness, these frames are augmented through techniques like rotation, noise injection, and mirroring. So these augmentations simulate real-world variations, ensuring the model can generalize well to diverse conditions. Second is we apply the Meta SAM model. For swimmers segmentation, the Meta SAM is a versatile model. It's capable of isolating objects in complex environments. By focusing on the swimmer, the SAM removes irrelevant background elements such as water reflections and splashes. So this process results in highly accurate swimming mass with an intersection over union IOU of 94%, demonstrating the model's robustness even in challenging aquatic conditions. The third is the segmented swimmer frames are passed on to the YOLO V8 model for the post estimation. So the YOLO V8 detects and labels 17 key joints, including shoulder, elbow, knees, and hips, with an average key point detection confidence of 90% of YOLO V8 excels in tracking swimmer movements. Even body parts are partially occluded or submerged. Then finally, we evaluate the pipeline's performance using standard metrics. So for our swimmer segmentation, metrics like IOU and false positive rate as assesses how effectively the swimmer is isolated. And for post-estimation metrics like detection accuracy and key point confidence measure the precision of joint identification. Together, these steps ensure a comprehensive and a reliable analysis of awesome emotions. So I would like to first show the video, visual examples of what is happening. So the SAM model, as we explained before, is used for the segmentations of the swimmers, despite the background images and the occlusion that causes the discrepancies. So as we can see, these are the each segmental model for backstroke, butterfly, and the breaststroke. Another visual example of what we can see is the post-estimation overlay of a YOLO V8 model. As we can see, after we segment the swimmers using the SAM model, we are pausing on to the YOLO V8 for the identification of 17 key points and the alignment of each body parts. As we can see, these are also done for backstroke, butterfly, and breaststroke. Next is our video identification of the each different strokes. As we can see, the YOLO V8 model is able to identify all the different joints of a person, and which helps in analyze the alignment of each different swimmers. This is a butterfly stroke. So we can see that even though it's very tough, but the YOLO model can actually segment it for certain frames that makes the analysis more better. Yeah, and this is the backstroke. And this is the backstroke. As we can see, the YOLO V8 model is able to identify 17 key joints of different stroke techniques such as breaststroke, backstroke, and butterfly, and also it can identify it. Let's go for the result overview. So let's see what are the results achieved by this pipeline, and what are the main results of. So this integration of SAM and YOLO V8 proved to be highly effective in addressing these challenges of underwater motion analysis. So for a swimmer segmentation, MetaSAM consistently delivered an average IOU of 94%, and this metric indicates that the model's ability to accurately isolate swimmers from complex aquatic background, even in the presence of occlusions like splashes and bubbles. In terms of post-estimation, the YOLO V8 identified and labeled 17 key joints with an average reduction of confidence of 90%. This performance is remarkable, and particularly in scenarios where the body parts are partially submerged or obscured in environmental factors. The data augmentation played a critical role in enhancing the pipeline's performance. Techniques like rotation transformations, noise injections, and mirroring improve post-estimation accuracy up to 12%. So demonstrating the importance of robust pipelining and the pre-processing, which helps in achieving a higher result. Finally, a comparative analysis. We have a comparative analysis as well, which reveals the difference between the previous model of YOLO V8 and the new proposed model of SAM segmentation and YOLO's post estimation. So as we can see, Rayo was able to give a 94 percentage more greater than the YOLO's V7. And this is also observed in many factors like many metrics like key point confidence, detection accuracies, and false for positive rate as well. As we can say, a key notable point of SAM plus YOLO V8 model is that we are able to achieve a minimum false positive rate of 2% while compared to the baseline model, that is the previous model of YOLO V8. So, yes. So as I like to conclude my project, as we are able to see how we developed our robust pipeline by integrating the Meta SAM and YOLO V8. Also, by implementing this, we are able to achieve a segmentation accuracy of 94% of IOU and a post-estimation confidence of 90%. We also addressed what are the traditional challenges and how this model of combining both deep learning model makes it better for people for making a better alignment and improving the track efficiency of swimmers as well. So the future directions would be real-time feedback system where we're able to analyze it real time by just scanning these videos, and also multi-swim analysis where you're able to analyze multiple swimmers at the same time rather than just focusing on one person and segmenting and and doing analysis for them. And also we can also make deep analysis on each of the person's stroke efficiency as well as the joint angles. Thank you.